Hello everyone. Welcome to this mini explainer. Today we're diving into an interesting electronics project, the PN sequence generator. This project is proudly done by students from Government Polytechnic Ratnagiri, Zishan Shaikh, Imran Shaikh, and Zaid Wasta. Before we get into the circuit, let's understand the theory behind a PN sequence generator. PN stands for pseudo-noise. A PN sequence is a binary sequence that appears random, but is actually generated in a predictable way. It's widely used in digital communication systems for spreading signals, encryption, and error checking. The PN sequence is generated using linear feedback shift registers, or LFSRs. These are basically a series of flip-flops connected in a line, with some of their outputs tapped and fed back through XOR gates. The feedback mechanism ensures that the sequence repeats after a certain period, but until then, it behaves like random noise. That's why it's called pseudo-noise. The key features of a good PN sequence are: it has a long period before repeating. It has nearly equal numbers of ones and zeros. Its autocorrelation property makes it ideal for signal processing. Now that we know the theory, let's take a closer look at how the circuit brings this to life. Now, let's take a look at this circuit. A PN sequence generator circuit uses shift registers and XOR gates to produce a repeating binary pattern. Here's how it works. The circuit includes a shift register made up of flip-flops. Some of these flip-flop outputs are tapped and fed into an XOR gate. The output of the XOR gate is then fed back into the input of the first flip-flop. With each clock pulse, the bits shift, and the XOR logic creates the next bit of the sequence. This produces a long sequence of binary values, the PN sequence, which is very useful in applications like CDMA and error detection. Now let's look at the truth table of our PN sequence generator. We're using a 4-bit shift register starting with the value 0001. Each time the clock pulses, the bits shift to the right. The new bit added on the left comes from the XOR of Q3 and Q4. That's what you see in the mode.2 adder output column. From this, we get a new state every time. The last column shows the PN sequence, which is taken from Q4. After 15 steps, the same sequence repeats. So even though it looks random, it's actually a fixed pattern. So that's the PN sequence generator in a nutshell. A simple yet powerful concept in digital electronics brought to life by our brilliant diploma students. Thanks for watching, and remember, even random-looking numbers can have logic behind them.